Hello and welcome. In this video I'm gonna show you some examples of limits that are in the forms of 0 to the power of 0, infinity to the power of 0, or 1 to the power of infinity. Before I solve the first examples for you here, first I want to show you the general process for solving these type of limits, and then we solve some examples together. If first we look at the general process of finding these type of limits, solving examples becomes much more easier and makes more sense. General forms of limits that led to these indeterminate forms is limit of f of x to the power of g of x and x approaches a, which a can be any number or infinity. The problem that we have in solving these type of limits is that we cannot use L'Hopital's rule for solving them right away. So somehow we have to convert them to a form that we can apply L'Hopital rule. And to do so, we use ln. Before I show you the process of finding these type of limits, let me remind you the properties of ln that we need here. We know that if we have something like ln of a to a power of say p, we can bring the power p to the front of ln and write it as p times ln of a. Another property of ln is that if ln of a will be equal to something like b, we can get rid of ln in the left side and we have a equals e to the power of b. And the last property that we use here is that e to the power of ln of something equals that thing. For example, e to the ln of a equals a. E to the ln of any expression equals that expression. E and ln are inverse function of each other and they cancel each other. E to the ln of any expression equals itself. So we need these properties. Let's start to see how we can find these type of limits. The first step is to name expression in front of limit something like y. So we name f of x to the power of g of x y. And then we take ln from both sides of this relation. And we get ln of y equals g of x times ln of f of x. We bring the power g of x to the front of ln. We use the first property that I mentioned here. And then we take limit from both sides of this relation. Limit of x approaches a of ln of y equals limit of g of x times ln of f of x as x approaches a. To find this right limit, limit of g of x times ln of f of x when x approaches a, we use L'Hopital rule and we can find this limit. Suppose after we use L'Hopital's rule, the value of this limit equals something like a. So we have limit of ln of y as x approaches a equals a, capital A I mean. So we have limit of ln of y as x approaches a equals a. Because limit of ln of y when x approaches a equals capital A, we can say limit of y itself when x approaches a equals e to the a. Here I use the second property that I mentioned here. Note that y is f of x to the power of g of x. So limit of f of x to the power of g of x when x approaches a is e to the a. And it means that our original limit equals e to the power of a. If you don't like this conclusion here, that from limit of ln of y equals a, we concluded that limit of y equals e to the a, You can do it in more mathematical way like this. We have limit of x approaches a of ln of y equals a. And we want to know what is limit of y when x approaches a. Here we use the third property. We know that e to the ln of any expression equals itself. Instead of y, I write e to the ln of y and x approaches a. So instead of y, we write e to the ln of y. We know that e to the ln of y is y. When x approaches a, limit of ln of y is a. So we can replace it with a and we get e to the a. So limit of y actually when x approaches a equals e to the a. This is the more mathematical way of proving this conclusion. Now that we know the general process for finding these type of limits, we can find these type of limits much more easier. We can summarize the process of finding these type of limits in these 4 steps. The first step is to name expression f of x to the power of g of x, something like y. And then we take ln from both sides of this relation and we get ln of y equals g of x times ln of f of x. Then we find limit of g of x times ln of f of x as x approaches a. And if we suppose this limit equals a, then our original limit, which was limit of f of x to the power of g of x as x approaches a, will be equal to e to the power of a. Now let me show you some examples to get more familiar with these 4 steps. The first example is limit of x to the power of 1 over x as x approaches infinity. If we plug in infinity for x, we have infinity to the power of 1 over infinity. We know that any number over infinity approaches 0. So we have indeterminate form infinity to the power of 0. The first step is to name expression x to the power of 1 over x, something like y. So we suppose x to the power of 1 over x to be y. And then we take ln from both sides of this relation. If we take ln from left and right side of this relation, we have ln of y equals 1 over x times ln of x. Now we have to find limit of 1 over x times ln of x as x approaches infinity. So we want to find limit of 1 over x times ln of x as x approaches infinity. To find this limit with L'Hopital's rule, first we rewrite 1 over x times ln of x in the form of ln of x over x, and x approaches infinity. To find this limit with L'Hopital's rule, we take derivative of top and derivative of bottom separately. Derivative of x in denominator is 1, and derivative of ln of x in numerator is 1 over x. And because x approaches infinity, 1 over infinity equals 0, and 0 over 1 is 0. So limit of 1 over x times ln of x as x approaches infinity is 0. So a is 0. If I want to compare this general process with this example, a is 0. And because a is 0, limit of x to the power of 1 over x, limit of x approaches infinity of x to the power of 1 over x equals e to the power of 0. E to the a, which in this case is e to the 0. And we know that any number to the 0 is 1. So limit of x to the power of 1 over x when x approaches infinity equals 1. If you like to write this last step in more mathematical way, you can do it like this. Limit x approaches infinity of x to the power of 1 over x is limit of y x approaches infinity. Note that y is x to the power of 1 over x. And we can rewrite e to the ln of y instead of y. We know that e to the ln of y is y. And here we prove that limit of ln of y when x approaches infinity is 0. So this equals e to the 0. And this becomes 1. Now it depends to you that you prefer to use this shorter method for writing your final answer, or you prefer to write all the steps and do it in more mathematical way. Another example. Limit of 1 plus x to the power of 1 over x as x approaches 0. First, we have to plug in 0 for x to see what type of indeterminate form is this limit. If we plug in 0 for x, in the bracket we have 1 plus 0, which is 1, to the power of 1 over x, which x approaches 0. We know that when x approaches 0, 1 over 0 goes to infinity. So this limit is in the form of 1 to the power of infinity, which is an indeterminate form. To find this limit, we name 1 plus x to the power of 1 over x y, and then we take ln from both sides of this relation, and we get 1 over x times ln of 1 plus x. To find limit of 1 over x times ln of 1 plus x as x approaches 0, we use L'Hopital's rule. First, we write it in fraction form, and then we take derivative of top and derivative of bottom separately. Derivative of x in denominator is 1, and derivative of ln of 1 plus x is 1 over 1 plus x. We know that derivative of ln of something is 1 over that thing. So derivative of ln of 1 plus x is 1 over 1 plus x. And of course we have to multiply it by derivative of inside, but derivative of 1 plus x is just 1, and we don't need to multiply it by 1. Now if we plug in 0 for x, we have 1 over 1 plus 0, which is 1. So in the numerator we have 1, and in denominator we have 1. So this limit equals 1. Because limit of 1 over x times ln of 1 plus x is 1, so our original limit is e to the power of 1, or e, because e to the 1 is e. Another example. We want to find limit of x to the power of 1 over x minus 1 as x approaches 1. First, we plug in 1 for x to see what type of indeterminate form is this limit. If we plug in 1 for x, we have 1 to the power of 1 over 1 minus 1. 1 minus 1 is 0, and 1 over 0 is infinity. So the limit is in the form of 1 to the infinity. Again, we name expression in front of limit something like y, and so we have y equals x to the 1 over x minus 1. If we take ln from both sides of this relation, we get ln of y equals 1 over x minus 1 times ln of x. Now we have to find limit of 1 over x minus 1 times ln of x as x approaches 1. Limit x approaches 1 of 1 over x minus 1 times ln of x. And we can rewrite it as ln of x over x minus 1 as x approaches 1. If we use L'Hopital's rule, we get derivative of bottom x minus 1 is just 1, and derivative of ln of x is 1 over x. If we plug in 1 for x, we have 1 over 1, which is 1. So this limit equals 1, and so the original limit that we are looking for equals e to the power of 1, or e. Let me show you another example. Limit of cosine of x to the power of 1 over x to the 2 as x approaches 0. This example seems a bit more difficult. First, we have to plug in 0 for x. If we plug in 0 for x, we have cosine of 0. And we know that cosine of 0 is 1 to the power of 1 over 0 to the 2 is 0, and 1 over 0 is infinity. So this limit is in the form of 1 to the infinity. First, we name cosine of x to the power of 1 over x to the 2, y, and we take ln from both sides. And we have ln of y equals 1 over x to the 2 times ln of cosine of x. Now we have to find limit of 1 over x to the 2 times ln of cosine of x with L'Hopital's rule. So we want to find limit of ln of cosine of x over x to the 2 as x approaches 0. We have to take derivative of top and derivative of bottom separately. Derivative of bottom x to the 2 is 2x, and derivative of ln of cosine of x is 1 over cosine of x times by derivative of inside. Derivative of cosine of x is negative sine of x. Let me remind you that derivative of ln of something is 1 over that thing. So derivative of ln of cosine of x is 1 over cosine of x. Don't forget to multiply it by derivative of inside. Derivative of cosine of x is negative sine of x. You can find this last limit in different methods. For example, you can use these facts about limits of trigonometric functions. Limit of sine of x over x as x approaches 0 is 1. And also limit of tangent of x over x as x approaches 0 is 1. Or you can write sine of x over cosine of x as tangent of x and do L'Hopital's rule again. It depends which method you prefer to use for finding this last limit. Here I am using L'Hopital's rule because this video is about using L'Hopital for finding limits. First, we rewrite sine of x over cosine of x as tangent of x, so numerator becomes negative tangent of x over 2x. We have a negative in top, and sine of x over cosine of x is tangent of x. We have this relation in trigonometry. Tangent of x is sine of x over cosine of x. Now we do L'Hopital's rule again to find this limit. Derivative of 2x in denominator is 2, and derivative of tangent of x is secant squared of x, and we have a negative in the front, so it becomes negative secant squared of x. If we plug in 0 for x, secant of 0 is 1, 1 to the 2 is 1, negative 1 over 2. Note that secant of 0 is 1 over cosine of 0, and cosine of 0 is 1, so it becomes 1 over 1. Note that at this step that we get negative tangent of x over 2x, you can use this fact that limit of tangent of x over x as x approaches 0 is 1 to find this last limit, and you get the same answer, negative 1 over 2. So limit of cosine of x, or original limit, to the power of 1 over x to the 2 as x approaches 0 is x approaches 0 of cosine of x to the power of 1 over x to the 2 is e to the negative 1 over 2. Or if you like, you can rewrite your answer as 1 over square root of e. Let's do another example. Limit of sine of x to the power of tangent of x as x approaches 0 from the right. First we plug in 0 for x and we get sine of 0, which is 0 to the power of tangent of 0, and we know that tangent of 0 is also 0. So this limit is in the form of 0 to the power of 0, which is an indeterminate form. To find this limit, we name sine of x to the power of tangent of x y, and then we take ln from both sides of this relation, and we get ln of y equals tangent of x times ln of sine of x. Now we have to find limit of tangent of x times by ln of sine of x as x approaches 0. To find this limit with L'Hopital's rule, we have to move one of the expressions tangent of x or ln of sine of x to the denominator to make it like a fraction, and then we can use L'Hopital's rule. And we know that usually we don't move ln to the denominator, so we keep ln of sine of x in top and we move tangent of x to denominator. If we move tangent of x to the denominator, it becomes cotangent of x. Because to move tangent of x to denominator, we have to write 1 over tangent of x in denominator. But 1 over tangent of x is cotangent of x. We know this relation in trigonometry. Cotangent of x is 1 over tangent of x. So instead of writing 1 over tangent in denominator, we write cotangent of x. Now we have a fraction and we can use L'Hopital's rule. We have to take derivative of top and derivative of bottom separately. Derivative of cotangent of x is negative cosecant squared of x. And derivative of ln of something is 1 over that thing. So derivative of ln of sine of x is 1 over sine of x. Multiply it by derivative of inside. Derivative of inside, which is sine of x, is cosine of x. Before we plug in 0 for x in top and bottom to find the limit, first we have to simplify this expression. Note that cosecant of x is 1 over sine of x. This is the definition of cosecant of x. It's reciprocal of sine of x. 1 over sine of x is cosecant of x. So I am replacing cosecant of x in denominator with 1 over sine of x. And so cosecant squared of x is 1 over sine squared of x. So we have limit x approaches 0 from the right. In top, we have cosine of x over sine of x. And in bottom, we have negative 1 over sine squared of x. Cosine of x over sine of x divided by negative 1 over sine squared of x is cosine of x over sine of x multiplied by reciprocal of denominator, which is sine squared of x over negative 1. Now if we divide sine of x from top and 1 sine of x from bottom, we get to this expression. Limit x approaches 0 from right, so we cancel 1 sine of x from top. In numerator we have sine squared of x. We cancel 1 of the sine x from top with sine of x from the bottom. And we have negative sine of x times cosine of x. And in denominator, everything simplifies. Now if we plug in 0 for x, we get the value of the limit. Sine of 0 is 0 and cosine of 0 is 1. 0 times 1 is 0. So the value of this limit is 0. Limit of tangent of x times ln of sine of x as x approaches 0 is 0. And so our original limit, which we are looking for, will be equal to, so limit of sine of x to the power of tangent of x as x approaches 0 will be equal to e to the power of 0, which is 1.